talk. Thank you, Via, for that. I would like to hand over this to Sabhrant Bhaiya now. Bhaiya, you can start. And welcome
Thank
back. Welcome, everyone.
thank you, Devashish. Good evening, everyone. So today we'll talk about numerical methods and analysis. So before we actually talk about this topic, I want to tell you guys why I actually picked this. So in most of my years of experience with IISER Bhopal, I have noticed that there have been numerous talks in pure mathematics. So mathematics as a whole actually can be divided into three parts, which are pure maths, probability and statistics, and applied mathematics. So most of the talks are actually from pure maths. You will see emails of topology, algebraic number theory, and other topics. But what this institute is currently missing are these two major other fields inside mathematics. So recently we have seen a few faculties that have joined. So Dr. Ambuj Pandey, he works in applied mathematics, and Karthik Adhikari sir, he is the only professor here in IISER Bhopal for probability and statistics. So I thought that this topic actually deserves some time because we use programming so much nowadays and calculations too. So this will be helpful to a wide variety of people, even who have not taken mathematics as their major but do programming a lot. So, and this is an informal talk. So feel free to question me if you are stuck somewhere. So now let's,
Sir, I mean
yeah,
Bhaiya.
just call me Bhaiya, please.
Actually, by the title, I thought it is a very formal club. I mean, kind of lecture.
Oh, I'm not a professor, so I don't like I'm not entitled to give you a lecture. I don't have that much of experience to give you a lecture. I'm just telling you guys what experience I have with applied maths. It has been only 1 year since I have touched this topic. Before that, I've just done courses in pure maths. There are very few courses in applied maths in IISER Bhopal. I think there's only one course called numerical analysis. All the other courses up till third year are its prerequisites, but yeah, I don't have that much of knowledge, but I can tell you all the experience that I have gained in the past 1 year of my thesis.
Okay.
This is kind of informal plus formal. I mean, this is a maths club talk. There are no professors here to judge you. Um, so yeah, please feel free to ask these questions. So let's move on to the topic. So we'll start off by solving a quadratic equation. Many of you have probably seen this in your class 12th or 11th, that you have to write a program to solve a quadratic equation where a is a non-zero real number and b and c are real parameters. So a standard way to solve this is first we compute the discriminant, which is v square minus 4ac, and depending on the sign of this discriminant, we calculate its real roots. So if d is less than 0, there are no real roots. Otherwise, we print these two real roots, r1 and r2. And to verify whether they are correct or not, what we do is we compare these with 0. So if these are 0, these are indeed the roots of our quadratic equation. So good enough. So let's plug in some values. So if you plug in a is 1, b minus 5, and c is 6, we expect the machine to give us 2 and 3, which it does, and for which the function values are 0. Okay, so the code is working as we wanted it to. It gives us the roots. So what's the problem with this? The problem is that for some extreme values, one of which that I've constructed is A1, B 20,000, and C 10 to the power minus 9. And since there are no bounds on B and C, this is one legitimate parameter that the machine can receive. So what should we expect the machine to give us? And notice that by no means these are extremely large or small numbers for the machine, because the double data type in MATLAB has ranged from 10 to the power minus 308 to 10 to the power 308. So these numbers are not too large or not too small for the machine. Maybe for us it is, but For the machine, it's not. It can perfectly handle these type of numbers. So what we see is that it gives us the two roots as minus 20,000 and 0, which is definitely incorrect. Because if you plug in these values back in the function, you get the value of C. So what is happening here? Why is this incorrect? So let's see why we get this. So if you actually solve this by hand, these are the two roots, two approximate roots, which get us as close to 0 as possible, which are more accurate than what the machine gives us. So if you calculate it by hand, you need the approximation that for small values of x, this can be written as 1 plus x by 2. These are not the exact values of the roots, but these are the best that we can do. And these are actually small enough. These are less than 10 to the power minus 16, which we're like, this is very small. But the machine is giving us something much more worse. It's giving us 10 to the power minus 9 instead of giving us 0. So we need to know why this is actually happening. So our algorithm is actually quite small, so we can see that there's nothing wrong in it. So we'll see that the arithmetic that goes on in a computer is generally inexact. It's not accurate. And the reason for that is that every number is represented only a finite number of bits or a finite number of binary digits. It can't compute any operation with that accuracy that we expect in theory. So to see this, let me introduce you to the concept of machine epsilon. It's the largest number in which the largest number x, yeah, it's the largest number such that if you add 1 to it, the machine cannot distinguish between 1 and 1 plus u. So for a machine, it will be the same, but in theory, they're extremely different. I mean, they can't be the same, right? So in the case of MATLAB, so all the outputs will be in MATLAB R 2020. I think the same also works for C++ and C. The machine epsilon might change in that case, or it will be something around that. So for this machine epsilon, what happens is that if you add u to it, so for this machine epsilon, we know that 1 plus u is exactly 1. So if you add in this particular way, so 1 plus u is 1, and if you again add u to it, it will again be 1. But if you add the exactly same thing in a different way, so first you add the two u's together. So now this number is bigger than machine epsilon. So it will not be again 1. So this shows that associative law doesn't quite hold when you're doing arithmetic in a computer. So any questions till now? This is already something quite big. Probably you guys didn't know this.
Yes, sir. I'm not unable to. I mean, I am unable to understand what is going on here.
Sir, is it due to that machine find an approximate value of in decimal point?
Yeah, so the machine actually uses binary. Most of the machines use binary, and there are certain binary bits that it can store, beyond which it doesn't store the bits. So it kind of truncates at some point, and then it gives up. That is why this is happening. 10 to the power minus 16 is too small for it to comprehend. Like, I mean, it can store it, but if you add this to it, like we'll see why this happens, we'll see. So if you don't understand, don't worry, we'll see about this. So this is about addition. So we saw that associative law in addition doesn't hold, but it's quite stable. I mean, if you're adding 2u to it, it's not equal to 1, we understand now. But the difference between this quantity and 1 is very small. It's just 2 into 10 to the power minus 16. It's not that big. It's stable. So now we'll talk about subtractions. Does the same stability follow in subtractions? So we are adding two numbers which have the same sign. Now we'll add numbers which have the opposite sign. So we were having issues when we were adding a number with a very small number. But in subtractions, the problem arises when we subtract numbers that are very close to each other. And that is commonly known as catastrophic cancellation error. So to illustrate this, what I'll do is, in fourth grade style, I'll subtract two numbers. So these bars represent that, it's just for you to easily see that there are 3 digits here in between each two bars. So there are total 1, 2, 3, 4, 5. So there are total 15 digits after the decimal point. And this one is at the 9th place. This is at the 9th place. So now if we subtract 1 from it, and the fourth grade style, what we'll get is, we'll get a 1 in the 9th place and then zeros everywhere else. Nothing too complicated yet. But the computer doesn't store the number in that way. What it stores it in this form: a times some exponent with some power. So it will bring this 1 after the decimal point. So we know that after 1 there are 6 zeros. So it puts 6 zeros after that 1. And since the 1 is at the 9th place after the decimal point, it gives the power 10 to the power minus 9. But what about these digits? What happens here? So it's actually...
Sir, why there should be any digit?
Yeah, because so MATLAB works with 16-digit precision. 16-digit precision. Which means that any number which is of double type will have 16 digits plus some exponential. So it will have to put some digits there. So we already know that after 1, the 6 digits are 0. What about the rest 10? Or sorry, 9, because this is the first. So first 7 digits are known. What about the rest of the 9 digits?
Are they 0?
0.
Yeah, that was my first guess as well, but it's actually garbage. The computer doesn't know what to put there. So it puts anything there. 9, 4, 3, anything.
That will create very much errors.
Exactly. So you only have 7 digits of accuracy now. You lost all the other 9 digits.
No, if it is unknown, why not put 0? Why put any other digit?
Yeah, actually, I don't know why all the programming languages are created like that. I also thought, why not 0? But it just puts garbage value there. It doesn't know what to put.
I mean, totally random.
Not totally random. I mean, if you do this process again and again, you'll get the same digits here.
How and why?
So we
Oh my
lost.
God, that is a big problem.
Yeah, that is a big problem. So these errors actually are very subtle. When you're programming, you won't actually notice these things. You'll see, okay, the output is not as you expected it to be. So there might be some fault in your algorithm, or there is some kind of bug that is creating this issue. So these errors are very subtle and they are not very easy to find. So these cancellation errors happen when you're subtracting two numbers that are very close to each other. In this case, we are losing all the 9 digits after the first 7. So only 7 digits of accuracy we get after the subtraction. And if you're using this number again in your algorithm, the accuracy even gets worse. So to illustrate this further, let's take this function f. So its domain is all positive reals. But if we rationalize it, we can write it as this function g. So in theory, these functions f and g are exactly the same. There is no difference. You're just rationalizing it. But there is a huge difference between these two functions in a computer. So if you evaluate it at certain points, so this is a graph that I plotted. On the y-axis, we have the difference between these two functions, the difference of the absolute. And then we have the x that varies from 0 to 10 to the power 6. So first million integers. And as you can see, there is quite a bit of difference. As the value of x increases, by the time you reach towards the end, you're only seeing that the value of these two function matches for the first 7 digits only. After that, it doesn't match. So if these two functions are the same, why are only the first 7 digits of the output are matching? What's happening with the rest of the digits? So as we can see that in the function f, as value of x increases, we are subtracting two numbers that are getting closer and closer to each other. If you calculate the limit of this term inside the bracket as x approaches infinity, it's tending towards 0. So what happens is there is cancellation error here. So there is error here. But it's magnified by this x outside. So what I'm implying here is that, for example, if you have calculated the value of pi very well up till 16 digits, so you know all the 16 digits here. And now I give you the exact value of pi, like in theory, you know trillions of digits of pi. So this is our approximated value of pi, and this is our exact value of pi. And now if you compute this, so let me call it pi 2. So if you compute 16, so if you know pi 2, which is an approximated of value of pi only till 16 digits, what would you expect this to be? Sorry, and then 0 in front of it, implying that the 16 digit was the same, and now the numbers are different. So basically, you get 1 digit of accuracy here. 1 digit. 1 digit is the same, the rest are different. Because we have multiplied a huge number to our approximated value. And this is exactly why the error is so large. Because we have multiplied x in front of it. If there was no x, probably it would have been still accurate. But because of this x, the accuracy is much worse. The same problem is not happening because of in this function g. So there is no cancellation error here. We are just adding two numbers which are close. That is not a problem. That is not something we should be concerned with. Because that is a stable operation. That will be accurate. So these functions are accurate in theory, but while computing, this function is much more accurate compared to f. Is it fine, guys?
Yes, sir.
Fine,
Sir,
okay.
because garbage number is not coming in GX.
Yeah, so there is no cancellation error here. So another example of error is the chopping error. So it is what it exactly sounds like. So after a certain point, it truncates the binary digits. It says, I can't handle any more digits. I'm only considering this much. I leave out the rest. So in these type of errors, some counterintuitive things happen. For example, this simple addition between these two decimal numbers is not actually equal to 0.3. And we'll see why this happens, but it's quite fascinating to see that the machine is not able to see that they are equal. And it also goes with the square root, because the square root of 2 is an irrational number, so it only sees the first 16 of it and stores it. The rest of it is discarded. So if you square it, it's not exactly 2. And my favorite example is this sum. So we are summing 0.1 k times, and we are subtracting it with k over 10. So in theory, this should always be 0. There is no difference between these two. But see what happens when I increase the value of k. As k becomes large, what happens is that this results becomes more and more inaccurate. We lose more and more digits while calculating this sum. And 0.1 seems like a harmless rational number. Like it's 1 over 10. It has only finitely many. It still has infinitely many decimal places, but it's repeating after a certain point. So we would expect it to be a little bit well behaved in comparison to irrationals, which doesn't have any repeating decimal places or decimal numbers. So these errors are actually troublesome. So in 1991, what happened is that a missile battery failed to intercept the incoming Iraqi missile. And this happened due to a chopping error. So what happened was, in the machine, 1/10 is stored as binary, and this is the expansion of 1/10 in binary. So in binary, this expansion is written like this. Should write in here. So this is in decimal places, and using this expansion, we can write its binary expansion. So its binary expansion is repeating. So this particular block is repeated again and again. And I've put a bar here to denote that the machine only took the first 24 bits. Or it took only these 24 bits and it discarded the rest. It didn't include these bits. So this induced an error. So this error is quite small. It's only this much in decimal. But missiles fly at extremely fast rate. I mean, it's in kilometers per second. This error is not in the speed, but it's in one of the calculations, which magnified the error. So the missile failed to intercept that Iraqi missile. So it hit actually one of their barracks. And all of this happened due to this truncation error. So that is why we saw why this sum and this simple sum is not exactly equal to our desired result. Because the binary expansion of 1/10 is cannot be exactly stored. This is known as floating point arithmetic. It's given a different name because it's not exactly arithmetic. Something different happens in machines. So now we know all these errors. So now let's go back to our question of explaining why we are getting this kind of a number from the machine. Why are we getting 0 and minus 20,000 when they are not the roots of the quadratic equation? So what happens is that b, which is 20,000, so if you square it, it is 4 into 10 to the power 8. And the other term, minus 4ac, so minus 4a is 1, so plus 10 to minus 9. So as you can see, this number is so large in comparison to this that the machine is not able to add this. So it says that this is insignificant for the first 16 digits of precision, so I'm going to ignore it. So the computation of D was inaccurate, because of which the rest of the computation was inaccurate. So while computing it by hand, we actually rectified this problem by considering the expansion of root 1 plus x, which for small numbers is 1 plus x by 2. That is why we have much more accurate results here. So far we have, so I hope this is now clarified. So far we have seen how to calculate the roots of a quadratic equation accurately. So for large numbers, we'll have to use a different approach. This approach will not work. And another thing to point out is that if the square root of D is very close to B, which in this case it is, the R2 might have a risk of cancellation error. So there is a possibility of cancellation error here if square root of D is very close to B, because you have B and minus B. So this approach is not the best, but it works in most of the cases. And another thing to point out is that as we saw, 0.1 plus 0.2, so floating point arithmetic, is not exactly equal to 0.3. So if you're comparing floats, this is a very bad way to do it. So if in your code you would have done f 0.1 plus 0.2 is equal to 0.3, do something here, else do something here. So this will, the computer won't actually go inside this if case. It will always go to the else case. So if you are comparing floats, this is not the best way to do it. The best way in this case will be to say that if f of R1 is less than some number, some tolerance, which you can specify, maybe 10 to the minus 15 is good enough, or maybe lower. If the value of f of R1 is less than this tolerance, we'll say that R1 is the root of this polynomial. And same thing goes for this. If you're writing equal to 0, then you'll never find the root of this function. In small cases, it might be, but not always. So now let's go to a more general polynomial, or a more general function, not even necessarily a polynomial. And let's see how we calculate its roots. So the method is called the bisection method, and it helps you to find the root of a function f. So the hypothesis for this is that f in this given interval AB should be continuous, and the sign of f of A and f of B should be opposite. It should not be the same. So since the signs are opposite, it implies that by intermediate value theorem, there must be a root between A and B. There must be at least one root. So now let's see how we find that root. So we define C to be the midpoint of A and B. And if the product of, so if FA and FC, if they have the opposite signs, we know that now the root is between A and C. And if it's not the opposite sign, we move on to the other interval. So in this first step, we have actually shrunk our original interval by half. So now that we know that instead of the interval AB, the root is in AC. So this tells us the root is an AC. So if we draw a diagram for this, so let's say the root is this red dot, and A1, B1 is our original interval. So first we take C to be their average, which is, let's say here, this is the average. And now we're see, okay, what is the sign of f of A1 and f of B2? Let's see what that sign is. So this sign is opposite. This means that the root is in this interval. It's not here. And we repeat this process. Now you take the average of these two, the average will lie somewhere here. Then you again check for the signs. It's negative here, so the root is in between this interval. And you again repeat this process, and each time you repeat this process, the size of that interval reduces by half. So we can actually see that there is some kind of approach towards the root. We are approaching towards something. So the algorithm, okay, is someone writing a question? Wait, I'll have to exit.
Sir, function had to be monotonic.
No, it's not. It doesn't have to be. It doesn't have to be monotonic. The hypothesis says it just needs to be continuous. So I think I know what question you have in mind. I mean, if there are multiple roots in this interval, what will happen? So we'll discuss this after the algorithm. So the first step is to initialize a variable k at 0 and take ck plus 1 as the average of the edges of the so we take the average of the edges, and after that we check the signs. So if they are the opposite signs, we take the appropriate next interval in which the root may be. And if it's the same sign, then it will be in the other half of the interval. And then we update the value of k and go back to step 2. So when should we stop this algorithm? So one way to stop this is that you can make a loop on the number of iterations. So you can say that maybe 100 iterations is good enough. So if your iterations, while your iterations are less than equal to 100, you continue doing this. Another way will be to say that if the function value at ck plus 1 is less than some tolerance, then we stop. Maybe if it's less than 10 to the power minus 14, you'll stop the code. So these are two ways to stop this algorithm. Yeah, so now let's talk about its limitations. So it actually works quite well. So I'll show you a few examples where it works nicely. So if you want to write a program to find the roots of a polynomial in some interval, this will work nicely. Given that the interval is small enough, if it's quite large, then it will require more iterations. Another problem that I've seen in junior classes is that they ask you to find the square root of a number without actually using the math library that you have in your programming language. So in both of these cases, what you do is, so in the second case, so if you have any polynomial, then you define f to be that polynomial. Otherwise, if you need to find the square root, let's say you need to find the square root of 2, you just define the function as x square minus 2 in the interval 0 and 2 and let that algorithm run. So while coding in MATLAB, I've actually put both of these conditions. This is just a failsafe. Maybe for some kind of functions, it is possible that I never reach this kind of tolerance. It is possible that the best accuracy I can get is 10 to the power minus 14. And then I check my errors, how accurate the result is. So bisection methods it works very well and it has a fast convergence as well. But there are a few limitations to this. And the largest one, the biggest limitation of this algorithm is that how do we find this interval? So if I give you a function, how do you find this interval? You have to take a guess at it. There is no algorithmic way to find this interval. You have to, it will be very costly. And the other one is that what if there are multiple roots inside the interval AB? For example, I can give you x square minus 1 in the interval minus 2 comma 2. So the algorithm actually will pick one of the roots, and we cannot choose which one it picks.
But sir, we can do like that. We find one root and then apply this root to other side and then find the other root.
Exactly, yes, that is one way. But you need to know what that midpoint is, which is between those two roots. So these are easy
Once
functions.
we find that root, one root, we can do it for other root.
Yeah, that is one way, yes. So you're using the fact that you know that there are two roots here. That
Yeah,
makes it
that
easy
will be
to figure out, yes. That makes it easy to figure out what to do next. So this is a bisection method in short. So there is some analysis involved, but it requires too much time to cover in a small talk. So the analysis that we can do further is, okay, how much accurate it is? What is the error involved in this? Let's say you stop at 10 iterations, then how accurate will the result be? And then that is the error. And then the next analysis that you can do on this is how fast it converges. Is it fast or slow? Do we require more iterations to reach to our root, or is it extremely fast? Sadly, I don't have enough time to. You guys, like, I've already given you 2 classes of content in this small talk. So I thought it might not be a good idea to go into further analysis. So I'll show you a few results after this. So you must have heard of the Navier-Stokes equation. And one of the most common ways to solve partial differential equations is using finite element method, which is known as FEM for short. So what happens in these algorithms is that you discretize your spatial and time domain into several discrete points. And maybe you can call that that gap to be h. And as you lower that gap h, the results become more and more accurate, but you are left with a large number of variables to deal with. But that is one common way to solve partial differential equations and integral equations as well. And this is the jet interaction. So if you let several airflows very close to each other, how will they react? Yes, so guys, that is all I had to discuss with you today. So I'll be happy to take some questions. I'm sure you guys have a lot of questions, especially with the starting part. That is the most complex one to understand. So any questions? Okay, Devashish, that's all I have.
Yeah, okay.